lot of the detail out of the chapter and basically summarize it in the 7 steps of contraction and relaxation, which is what we'll start on, look at. And then there's a couple of loose ends basically in the chapter to finish up. Okay, and that's the end of the new material. Then what I am going to do as far as how I'm going to review is I'm going to review a lot of Chapter 8. Okay, Chapter 8's not only the basis for everything that we're doing in this unit, but when you look at the critical thinking questions, most of them are going to kind of come from Chapter 8. Chapter 10, there's a lot of information about the senses, but they're pretty, it's a pretty straightforward, do you understand sensitive areas, low 2-point discrimination, high density receptors, do you just sort of understand it? So it's not that bad, and 12 is pretty straightforward too. So especially what I'm going to be doing in the beginning of Chapter 8, there's a couple concepts that are difficult that I know are on the test that I'm going to emphasize and make sure that we sort of, write new notes on it to really help clarify it. And again, that's what we're going to do first as far as that goes. So then, depending on the time where we are, again, you're going to see that answers a lot of the critical thinking questions on that first page. We can then do, we can see exactly what we want for the people that are left. I mean, we could, I depending on the time, I sort of like kind of doing Chapter 10 or doing the drugs maybe next to review that, and then Chapter 10, and then you can see the questions on the second page that sort of correspond. There's really no need to do much of 12. It's sort of, here's the main bulk of it anyway. So that's the goal. So, okay, we're going to go here. So here are the steps that I put on. We're going to go through with some pictures here, and really this is sort of it, something for, for you to sort of understand and somewhat memorize. So muscle contraction, relaxation. There's all the steps, but we're going to go ahead and go through them using their figures a bit. And I'll go ahead and shut the light because I'm really not going to write. I'm not going to write anything on the board for these. It's sort of all written here. So we do know, and this is sort of an idea, when we're dealing now with skeletal muscle, we have a specific efferent. It's the somatic motor neuron. We have a specific neurotransmitter we release. That is ACH. What is ACH?
Acetylcholine.
Acetylcholine. Okay? We even know this from the video before I'll just go these steps in a minute. I just want to mention now. Acetylcholine is released, and neurotransmitters, when they're released in synapses, even neuromuscular junction, we have sort of 2 main controls. This is from the video too. We have the scissors, which are enzymatic degradation, and we have the reuptake pump. What does acetylcholine use? Scissors or reuptake? Scissors. So acetylcholinesterase, which isn't on this, but people were asking about it, so I wanted to put it on again. Basically, the motor neuron releases acetylcholine. The skeletal muscle releases acetylcholinesterase to control levels of acetylcholine. That's sort of, it's not listed here, but I wanted to mention it. That's sort of the control of that neurotransmitter in the neuromuscular junction. Acetylcholine being released, but we are using acetylcholinesterase that the skeletal muscle actually produces to control it. All right. And we can always revisit that. So here's the idea. We're going to release acetylcholine. It's going to cause a depolarization, a type of graded potential called an end plate potential, because that's where it's sitting here. That's going to lead to an action potential. Okay, you can see it's still sodium, potassium, etc. Action potentials are going to travel all along the sarcolemma, including spreading down to these T tubules. Once we get to the T tubules, there's a specific receptor that gets activated that are on the T tubules called the DHP receptor. The DHP receptor does something very important. It's sort of somehow basically controlling calcium release from the sarcoplasmic reticulum. Calcium is the key for muscle contraction. It is sort of the idea that we have again, our simple circle of life, but the real key is, right now, so we won't even complicate it, there's very little cytoplasmic calcium available. It's mostly extracellular, but especially in skeletal muscle, cardiac muscle, etc., we have it's stored in the sarcoplasmic reticulum, okay, in this case. So it's in the modified endoplasmic reticulum, so the SR. And so the key is, as long as it's contained here, we're cool. But calcium has a lot of second messenger effects. If we release it, it's going to cause a bunch of effects. In this case, it's going to be the key ion, the key factor for muscle contraction. So, again, we had this idea, and then we'll actually continue on. We want to trigger a skeletal muscle to contract. The somatic motor neuron is going to release acetylcholine, cause an end plate potential, spread out to an axe potential along the sarcolemma. It's going to activate the DHP receptor to release calcium. Now, if you just read number 4, we're going to go to another one of their figures, which will help explain it. And this is just fun to say as you're walking down the street. Calcium binds to troponin. That's going to move this molecule tropomyosin that's been blocking the ability of this to interact. Then myosin can bind with actin and basically do the next step of the power stroke. So the step number 4 is best illustrated by their diagram here, so we can actually see this. And so if we look at the relaxed state, here's where we are. So the thin filaments were actin, but they had these accessory proteins that I said we were going to get involved with, and troponin and tropomyosin. So in the relaxed state, the idea is this tropomyosin is blocking the ability of myosin to bind to actin. Okay, partially blocking it. Okay, here's troponin with that little hole dying to have some calcium fill it. That's the relaxed state. That's when the calcium is inside the sarcoplasmic reticulum. But we just released it. And so what's going to happen is shown in this second part of this, where calcium is going to bind to troponin. That's going to move tropomyosin so that now myosin has a strong binding with actin, and we can do what we're going to do next, which is the power stroke of how it's going to ratchet it in. Okay? So that's why I had to sort of use both figures to illustrate this, because this illustrates point, and I'll come back to this. This illustrates number 4 really well versus their figure really didn't. What does that mean? Okay? So the DHP receptor releases calcium, but calcium is going to bind to troponin. Again, you have the words. Bind to troponin. That's going to cause a shift of tropomyosin, so we can have strong myosin-actin binding. And then we can do what we're going to do next, called the power stroke.
Because it's shifting what?
This guy is tropomyosin. It's been blocking it. It's going to cause a shift of that, so now myosin can bind to actin directly. So the relaxed state is blocking. Calcium is going to initiate with the help of troponin, moving it. So now we have strong myosin-actin binding, and we can do what we're about to do. So what are we about to do? Power stroke. It's like a new dance. Everybody do the power stroke. Now, again, the power stroke, if you look at the figure in the book, it's got like a lot of steps, and it's some very specific things. Again, since you're in class, you're listening to me, and really, I'm going to use the figure, really these 3 bullet points, which I'm going to describe, that's what we need to know about the power stroke. We're not going to need to know details of when does inorganic phosphate leave, or ADP, okay? I mean, basically, we're going to use energy to do this. Okay? So the very first thing I'm going to talk about is we're starting here. We've allowed strong binding, right? We just got rid of that tropomyosin. But the power stroke is this. If you look at myosin now, you see it's got this little hinge we talked about, but it also has another site besides its ability to bind actin here. These are actin molecules. It has an ATP binding site. Because to move something, we need energy, and that's ATP. So the first step of it is ATP is going to bind, and it really is going to do 2 things. Okay? One thing it's going to do, ATP is going to be used to release from the actin, and then the energy is going to be used to basically cock this back 90 degrees, and so it's sort of over the next outside actin. Okay? So it's going to cause release, and then cocking this 90 degrees. And here it is going. So again, we don't care the specific detail of how it's working, but now it's cocked and now it's on number 2. It was at number 1, ATP release, use that energy to put it over here. Okay? Now, if you have a spring that likes to be here, and you push it to here and let it go, what's going to happen? Okay? It's attached to 2. It's going to ratchet it in. Okay? What's going to happen next? ATP binds, release, cock over. Now it's on 3. What does it do then? Ratchet it in. So that's the power stroke. It's not as complicated as they sort of make it out. It's literally ATP binding, causing release, cocking at 90 degrees so it's to the next actin, letting it go, it ratchets it in. As long as calcium is present and we have ATP, that's what's going to happen. It's going to simply use it, cock it, number 3, use it, cock it, number 4. It's ratcheting the actin inward. We talked about the sliding filament theory, or that's what it's called, but really, again, it's a ratcheting type thing. We're not really sliding. We're getting cross-linking here, okay? And the actin is sliding inward, but it's really being ratcheted by this power stroke. As long as calcium is present, that's what's going to be happening, and ATP. If you go back a second. Okay? Looking at number 1, the way they say it, before we added ATP, again, this was tightly bound, okay? It needs ATP to unbind it. And they said the tight binding in the rigor state. What does rigor make you think of? Well, okay, well, everyone's got a different thought in their head. They're like, I don't know, what is rigor? Okay. For me, because this is the kind of guy I am, I think of, some people have said it, rigor mortis. Okay? Rigor mortis, okay, is bad, okay? So the idea of rigor mortis is when you're dead, do you have a lot of ATP? That's what rigor mortis is caused by. The fact is that without ATP, the myosin is unable to detach from the actin, and so you're in the state of rigor, which is what it is. Then, of course, everything degrades, and then everything get relaxed. But that's what rigor mortis sort of comes from, or why. Okay, but that's the power stroke. Okay, all you have to know about the power stroke is sort of what I said, not all the details of I don't know how many steps they have of this. You basically have ATP binding, causing release, and cocking at 90 degrees. Then, basically, it will come back to where it was, and now it's spread actin inward toward the M line. Okay, and then repeat as long as calcium is present. So we're to basically the last steps of relaxation. And so, 2 things, and that's it. This is this easy. Okay, we're going to pump calcium back into the SR, so everything resets. Okay, now you can't have any more cross bridging because that tropomyosin came in. Okay, and so we're not cross bridging anymore. We're up to here. But does this seem relaxed? No. So we have to somehow get back to where we were. Who's going to help us do that? Titin. Okay, this other protein, titin. Let's kind of look at it here. It's almost like we've been sort of compressing it. Okay, it's sort of like the spring idea. So that now if we allow it to release, it's going to spring back to its original sarcomere length. Okay, so the final 2 steps really are relaxation. We've got to put calcium back. Okay, so we don't keep doing the power stroke, and that stops us from cross-bridging more. But now we have to return back to the state we were, and that's that protein titin, again, that will help us get back to the original sarcomere length. Those are the 2 steps of relaxation.
What was the first one again?
Of relaxation?
Yeah.
Calcium pump back into SR.
Oh, okay.
So, you see this again? And let's just look at it again. This is really a lot of the chapter summarized. So, how do skeletal muscles contract, relax? First, acetylcholine is released into the neuromuscular junction, and it's going to end up resulting in an action potential that travels down, activates the DHP receptor to release calcium. Once calcium is released, it binds to troponin, moves tropomyosin. Now we have strong binding. Power stroke. Power stroke. The main points are up there. We're going to have ATP binding to myosin, causing 2 things. Release, energy cocking it back 90 degrees. We let it go, and boom, it's pushing it inward. As long as calcium is present, we're going to keep causing cross bridges, move these inwards. Relaxation. We'll get rid of that calcium, pump it back into the SR, and titin will help restore length. It's that easy. So when you have anatomy, you're like, hey, this is no problem. Any questions about that?
the energy is needed to bring it back to, or to cup it back to the 90-degree point.
Yes.
But the myosin is always moving anyway.
What do you mean moving?
One of the things move. Well, obviously the top thingy, but the way it gets from the one to the second one, and then the second to the third to the fourth, is it pushing the myosin along?
No, it's pushing the actin in. Okay, right now, of course, I do anything, but the actin is sort of coming in. The YouTube videos really help, right? But the actin's coming from the outside. It's literally pushing across. You know, the myosin's in the middle, the actin's on the side. It's pushing these actins inward. It's ratcheting this inward. This is basically 1, 2, 3. And so I wish, again, I don't have the internet here very easily. I put on, in fact, it's sort of here. But of course, you might even have better ones. There's a really good one. It's only like 3 minutes. A YouTube one that basically, instead of me doing this, it actually, and you have a ton of them out there, you actually see sort of it happen. Okay, and they'll actually, this one I like because some of these videos you have, it's on the PowerPoint that you have online. You can see it too if you don't want to write it down here. But in some of these ones, they're going to have too much, like more information than we need, and you're listening and like, what do you do? This basically just has exactly kind of what we just said, almost verbatim in a sense, but you get to visually see it move versus, it will make more visual sense. And again, if I had a long cord or something, I would just play it right now. It's like only like 3 minutes, but we don't. I don't know the new building if it has something called wireless. I'm not sure. I think they've heard of that. They spent a lot of money on this building. I hope they have something. Any questions about that? Okay, bulk of the chapter. Loose ends. Loose ends, and we can get going on sort of a review of the material. So, and really when it comes down to it, for the most part, what we did in the lab, we'll talk about this. It's going to be sort of part of this. So, here's the definition of a muscle twitch, and then the next figure really shows kind of what we want to get out of this, and you'll see how it relates to lab. So, the idea is, of course, as we're cross-bridging here, as an action potential, does what we just said, and we cross-bridge, we create tension in the muscle. That's what cross-bridging is. It's creating tension, which is power. But let's look at this figure. It's actually a really good figure because it's going to help us understand some differences between electricity and actual physical movement. So what this is we're showing the action potential in that somatic motor neuron. It should look familiar to us because we know what an action potential is in all the spaces. Remember, it's a couple milliseconds. Now, we just said that once acetylcholine actually reaches the sarcolemma, it's going to cause an action potential along the sarcolemma. Guess what? It looks similar, okay, not identical. And this is what I said, most of these action potentials, even the ones in the future, it's going to have very similar features to what we learned. Maybe the resting's different, maybe it doesn't have a hyperpolarization, doesn't matter. Depolarization, repolarization. What do you think is causing depolarization here? Sodium. What's causing repolarization here, you think? Potassium. Okay? It's going to be very similar to this. But, it's this thing turned off now. That's a couple milliseconds too. But that's electricity. Okay, when we're talking ratcheting in muscles, to do this and to do this, it's in milliseconds. Well, it is, but it's a lot longer. So this figure down here, the y-axis is showing the tension created by this, by one action potential spreading through. And it consists of this contraction phase in which we're cross-bridging, and then the relaxation phase in which we're pumping calcium back and tightens, restoring length. And this is much longer. Okay, maybe it's 50 times longer than this. That's electricity versus just physical movement. So what this does for us, for skeletal muscles, is make us think. What if we have action potentials that occur before this is fully relaxed? Can we create more tension in a muscle? More cross bridges, more tension, more power? What do you think? How many people think yes? Yeah, I think so too. Let's see. So, if they're far apart, if your action potentials are causing these twitches are far enough apart, the muscle fully relaxes again. No, we're not increasing tension. But if you increase them so that now they're going to occur before the muscle is fully relaxed, before we restore the sarcomere length, Now we're going to start doing it again. We're going to have more cross bridges, which create more tension in the muscle. Okay? Is there a maximum for our muscles? And we're going to call that tetanus. And I don't care, you know, unfused versus fused, so let's just put fused. The idea is, you know, there is a maximum number of cross bridges that a given muscle can actually have, and that's going to be the maximum amount of tension that can be exerted in this muscle. And so you can see we have a lot of action potential. So again, this is the idea again of summation, that if we have, for skeletal muscle, if you have action potentials that occur before muscle completely relaxes, it's going to build up cross bridges, build up tension, and create more force. And the maximum level that a given muscle can create is called tetanus. The muscle is in tetanus at that point. It's at its creating the most tension that it can create. Can we just hold it there forever? What if we're shouting, "Go! You can do it! You can do it!"
Yes.
No. Although some people did it a long time, like it was like 180 seconds. I don't know. There was some crazy stuff. Okay. But the bottom line is, your muscle will fatigue. So a couple slides on fatigue and slow, fast twitch, and then we're done. So the kinds of fatigue we have, there is central fatigue in which our brain does say, you know, this is not worth the grade. I'm letting go of this thing. All right. Or, you know, I don't need to run that extra mile. Whatever it is, the idea is our brain, and that's real fatigue because we can, you know, control it and try to, you know, counter it, etc. But that is central fatigue. You basically say stop. But the peripheral fatigue is more, you know, biochemistry, things going on. And so both, you know, a lot of this is in research, you know, specifically, but overall the idea is you either run out of stuff that you need or you start accumulating things which interfere. Okay, and both of these things actually are happening. And that's what will cause a muscle fatigue, the combination of these things. So you can lose, you know, you can make it where the, you know, you don't have enough acetylcholine anymore in your synaptic terminals, because, you know, you have to make that and put it there. You can run out. Or your muscles might run out of energy. And we're going to talk about energy in a second, because this is going to help us explain slow and fast twitch. So we're going to come back to that. So you can lose things you need, like energy or acetylcholine, or you start accumulating things which interfere with the muscle ability of the muscle to contract. And we've all heard of lactic acid, and, you know, lactate itself is not bad. Okay, because, you know, you get kinesiologists and all these other people all like throwing things at you because they're really hot on that. You know, everyone's got their little pet peeves. So we actually use lactate, but the idea is acid. So the idea is inorganic phosphate is acidic, and we're doing ATP and breaking it down. We are building up hydrogen ions. You know, we're causing too much potassium going out, etc. All those will interfere. Okay, and slow things down. So not enough energy or too much even acid. Energy. You don't care about that slide. Let me take that out. How does the muscle get energy? Well, the three sources, two of which we talked about a lot, you know, overall between this and other classes. ATP is the key, of course. Now, we can get ATP several ways. The idea is sometimes we need oxygen, sometimes we don't. For those few steps, we do not. And so when you're not using oxygen, it's anaerobic. And glycolysis, which are sort of the first steps of breaking down sugar, we talked about that before, that doesn't require oxygen. It's quick and it's anaerobic. But of course, you know, it builds up those toxic substances fast. So that's glycolysis. If you have a little more time, you can efficiently create more energy using this whole system here, and that's going to require oxygen at the end. And we'll revisit this for slow and fast twitch. I want to mention this guy because, you know, we always talk about this for cells, but skeletal muscles have a backup energy source stored in this molecule phosphocreatine. And so I want to show a picture of what that is. So the idea is this, that basically, you know, when you're sort of, you know, building up, you know, when you want to, you know, supply your muscles with as much energy as it can, part of it is we're going to take some ATP, combine it with creatine using this enzyme, and create phosphocreatine. The idea of that is now, when you need some energy, and I don't know why he needs this much for just the mow the lawn here, but when you need some quick burst of energy, we got one step. Instead of glycolysis, if you go back to it, it's like 10 steps. Cellular respiration, it's like 35 steps. Here we got some ATP in one step. Boom, ATP. And so that's the quickest energy that we can get. If you're talking about when it might be used, we only have maybe 5 seconds worth of burst energy from that. Okay, then you run out. We don't have a ton of phosphocreatine that we can store in our muscle. But we have a few seconds worth of intense exercise. So if you're doing, a fast jump, a fast move, or the fastest sprint you can, you'll probably use that up relatively quickly. Okay? But that is a third source of energy for muscles. So it's not just glycogen and using glycolysis or even aerobic respiration. They have a little bit of this phosphocreatine. Again, one step to get ATP. We have heard of slow twitch and fast twitch. There's at least 3 types. We could memorize table 12-2 or look at my table. How many want to look at my table? I want to look at my table. All right. So, again, all we have to do when we're doing this is sort of look at one, the other one's the opposite, this one's in the middle. So when you look at fast twitch, there's at least 2 types. One uses primarily glycolysis, which is fast. The other one sort of uses a combination of oxygen and glycolysis, depending upon the conditions. One primarily uses the oxygen, okay? And that's going to be important for understanding sort of how these relate to one another. So really, I'm looking at just 5 characteristics that are going to distinguish slow twitch and fast twitch. The first one, it's the slowest, okay? And all that means is when we're looking at the enzymes and various things of actually how fast these will contract and how fast that they'll relax, they're the slowest compared to these others. Okay, they're not the quickest to go. But the second one is it's like the yin and the yang. Their advantage is they're fatigue resistant. If you think about the muscles in my back supporting me, they don't have to be fast, but I want to just fall down after 5 seconds, okay? So I don't want them to fatigue. So you have a lot of slow twitch muscles in areas like your back support, muscles. Okay, so those make sense. Now all of these go together. Okay, all of these will go together. And I'll still keep the light off. I have enough because I'm not having much figures here. So they're going to use aerobic respiration. They're going to make primarily. These cells work really well using all the enzymes necessary for aerobic respiration, which is using oxygen, because they have time. Okay, and they won't fatigue because that's the best way not to fatigue. So we can go through all those steps. That's their main type of metabolism. These are related to aerobic metabolism. That's why these will go. So the idea of aerobic metabolism means we need oxygen. And we're going to talk a lot about respiratory system in the 4th unit. So we need oxygen. Here's our muscle cells. Okay? So 2 things about it. When you actually go back, and some of you have already done this, some of you will, when you talk about how we use oxygen for cellular respiration, we're actually going to use, and we actually just mentioned this when we're reviewing organelles. Oxygen is used in the organelles called mitochondria. We might have just memorized, mitochondria, energy production. That's how we're going to use oxygen to get ATP. So, if you're mainly using aerobic respiration, wouldn't it make sense that these cells would have a lot of mitochondria? And they do. If you're fast twitch, mostly anaerobic, you don't need as much, and they don't have as much. So having high amount of mitochondria fits that it's using oxygen. It's aerobic. If you train aerobically, your cells develop more mitochondria per cell. There's a lot of adaptation for training, and so that will make it more efficient. The next one. Sometimes we'll talk about red and white fibers. So, the slow twitch that we're talking about right now, the red fibers because they contain a lot of myoglobin, which is on the bottom here, which happens to be red color. Myoglobin fits this for the following reason. We're going to learn that oxygen, that gets into our blood, not very soluble, okay? It's a nonpolar molecule. It doesn't like water. We want to get it there. We're going to need a helper, and that helper is hemoglobin. Hemoglobin is going to carry that oxygen through the blood to the cells. Then it says, okay, I got to go back and get some more. So we got oxygen here. It's a long way from those mitochondria. We don't want to wait for it to fuse. We need hemoglobin's cousin to carry it to the mitochondria. Hemoglobin's cousin is myoglobin. Okay, so myoglobin is now picking up this oxygen and then carrying it to the mitochondria, because that's where we actually use the oxygen. That's why we have a respiratory system. It's the final step of producing ATP aerobically. And that's the only reason we need the whole respiratory system we'll talk about. But that's why all three of those go together. They use aerobic respiration, which means they need a lot of mitochondria, and to be more efficient, a lot of myoglobin, which is red, to actually transport the oxygen to the mitochondria. All of them make nice sense. Fast switch, exactly opposite. And of course, the ones in the middle are just in the middle. So it's really understanding one, and you've kind of got this idea. Three of them, again, related to metabolism. Any questions about that? Easy peasy. Okay, last couple slides. We did this in lab. This is, as far as lab goes, as far as the EMG lab, all we have to know is exactly these slides here. So, again, a motor unit is, just like we said before, it's on there. Basically, it's going to be the somatic motor neuron and the muscle fibers that it controls. Okay? Doesn't matter how you say it. They work together. It's the somatic motor neuron controls a series of muscle fibers. So, again, a motor unit, just one more time, just to say it a different way, because we're basically done then. So a motor unit is, just put it a different way, a somatic motor neuron and the muscle fibers that it controls. If you need to create more force, you activate more motor units. And that's just called motor unit recruitment. Okay, because more motor units will equate to a greater force. Everything else in that EMG packet, men versus women, all the factors about how we recruit motor units and all that, not on this test on Monday. Okay? After this test, we'll revisit all the lab stuff for the lab test, which will come up be our next test a couple weeks after that. Okay? Then we'll look all of our handouts, we'll fill them out that we've been getting behind on because we've been worrying about this. And when lab, we're going to make sure we know exactly what that test is. That lab test, not, well, I don't want to call it not critical thinking, but very straightforward. It's like I can literally take things from those lab sheets, put them on, except change the numbers. That's really what a lot of it is. It's that literal. That's why at that point you bring back those 6 lab sheets and we make sure we fill them in and we talk and make sure we know what's going on for that test. That's like 60 points. But that's after this one. So again, from that lab, again, all you need to know is kind of just lab. Any questions about chapter 12? Okay, so take 30 seconds, take a minute. We're going to review again chapter 8, but I'm going to be emphasizing a couple very confusing but important points that will help you get some of the critical thinking questions. And I'm going to be doing that with your help in a couple minutes.